Okay, hello everybody. My name's Angelina Ibay. I'm the team lead of this project. This is for ME 106, our Mechatronics semester project, and I have the rest of my members, including
My name is Vien Cantong.
My name is Diego Oliva.
I'm Phan.
I'm Benjamin Tran.
and this is our firefighting RC truck. So, just a little introduction. The main objective was to design and build a remote-controlled fire truck prototype that has the ability to not only detect flame temperatures, but to have our water-based turret system to aim at that heat flame and extinguish it. The overall design was to aim to support firefighting efforts in locations where human safety is ultimately compromised. So the main processes of this project included a tank drive that was remotely controlled by the user, our heat system or heat sensor system that included a thermal imaging camera and as well as other sensors, and our pump system that surrounded our turret system that ultimately points at our heat temperatures and extinguishes those flames.
Next up, we're going to talk about the microcontroller. So in our project, we decided to use an ESP32 microcontroller instead of the one given in lab, the Raspberry Pico. We chose the ESP32 compared to the Pico because one, we're trying to get sensors back from an RC core, which is being controlled remotely. So trying to display a web server through the ESP32 Wi-Fi module is doable, but it can't be done on a Raspberry Pico since it does not have a wireless Wi-Fi module, along with the ESP32 having a higher clock frequency, so it can process data much faster than a Raspberry Pico can.
All right, so these are the three sensors that we decided to implement for this project. We have the ultrasonic distance sensor used for obstacle avoidance and detection. We have the FSR 406 pressure pad that we use to measure the water reservoir levels. And then our main sensing technology is the MLX 90640 IR thermal imaging camera. This will be the main sensor that we used for the fire detection, and it helps to trigger the rest of the fire suppression system. So let's move on.
We use four main actuators in this project, one being the PMDC motor, which we pretty much converted to just a DC motor. And we use that to two of them to control how the tank drive through an electron speed controller. We also use a stepper motor to have the tank go through a horizontal pan, a 180 pan left to right to track or like to for it to find a where the flame is in its field of vision. We also use a servo motor for it to go up and down, tilt up and down, for it to angle the turret appropriately to target the flame, along with using a 4-volt DC pump, which alongside a relay module to activate it only when a fire is can be seen. So how this all works is by having the stepper motor do a 180 pan back and forth, and once it sees a fire in its field of vision, it stops it using inputs from the stepper motor driver. alongside the servo motor tilt axis being locked on into the flame range in its pixel array through the thermal camera. And then once everything is fully locked on, it triggers the relay module for the pump to be activated. And once the flame, it will activate the pump until the flame is no longer seen. Then it will continue back to its sweeping motion where the stepper motor is trying to find a fire in this thermal camera field vision. And next is the Aussie drive, where we just use a flat sky transmitter and a electronic speed controller, connect those to the two PMDC model mentioned before into a receiver, and then pair that to channel 1 and 2, and then sync it along each other, where the forward and reverse will be in sync with each other with 100% throttle input. Let's say for going right, we would have 50% throttle input on the right motor, but 100% throttle input on the left so that it is able to turn right, and vice versa for left.
Right, so here we have a comprehensive hardware wiring diagram mapping all of the components that, generally all of the components that we used for this project. As you can see, the RC drive system is completely separate from the other component integrations with the sensors and the other actuators. But this is just a comprehensive wiring diagram mapping the pinouts and all of the wiring configurations from the main microcontroller to the sensors, the actuators, the drivers, as well as the power distribution within the batteries and the power pack to each of the components, and as well as the specific pinouts for each of the components as seen here. So, yep.
Over here, we have what the web server would look like with all the sensors plugged in. Currently, it's not plugged in, but this is just a HTML format of everything. So in the center, we will have a pixelated array of the temperature scales between each pixels. And on the top right, we have the liquid ounce field gauge, which is detected via the pressure sensor pad, along with the ultrasonic distance, outputting the distance back to in millimeters, along with the FSR voltage, which is via the pressure pad mentioned before.
Other components that we used were tubings, water reservoir, and a custom track. The tubings that we used were used for the pump so that the water can be transported from our water reservoir and out of the turret that we used. Our water reservoir was approximately half a gallon, and it holds the water so that the tank itself can transport water to and out towards the place where the emergency would be. We have Diego to talk about the tracks.
Since this is supposed to be a scaled model of a real aided firefighter fire extinguishing tank, it is a better idea to use tank tracks instead of a typical wheel, because when there is such a great force due to the weight of the actual tank, this causes the wheels to sink into the ground. So that's why we opted for tracks instead. And with those tracks, we found a kit that has all the components we needed, and we integrated it properly into our system. These included the sprockets to drive the tracks and rotate the tracks, as well as the road wheels and idler wheel, which is the same wheel, but the road wheels are apply the tension to the track onto the ground, and the idler wheel just applies tension to the track so that it rotates smoothly.
As stated earlier, our turret will need to have a horizontal left-right motion and a vertical up-down motion. To achieve that without friction and to have a smooth motion without hurt damaging our motors, we had bearings for both the up-down motion and the left-right motion. The up-down motion for the turret, we used a bearing block that was 3D printed, and for the left-right motion, we used a different set of bearings so that it can carry the weight and the compression when the entire chassis is assembled together.
So over here we have a working web server of the Domo camera, and you can see I'm lighting up a lighter, and it's detecting that the lighter is in about 100 Celsius, but the farther you go away from the Domo camera, the worse the accuracy of the temperature reading is, which is a little bit of a drawback with using this Domo camera.
Next, we have a little demo of our pressure sensor. As mentioned, we use this sensor to indicate when our water reservoir was running low. In the video you can see that the LED kind of indicates that the water level of the reservoir is on the emptier side. However, as you fill up the cup, it turns off. This pressure sensor did require some calibration based off of the amount of water we were using. Um, the pressure sensor also worked with a simple volt divider. It usually works with a standard 10K resistor. However, through calibration and testing, we found out that using 2K resistors in series were much appropriate just so we can have a more accurate pressure differences in our water heights.
And then this is our demo of the pump working. As you can see at the bottom, it is our water reservoir. And with the use of the pump being powered, we have a steady stream of water being used and shot into the sink.
And this is a demo of the tank drive working, going over an obstacle of a couple blocks. These blocks were about half the height of the tracks, which shows its ability to maneuver around rough terrain and move around rough terrain reliably. All right, to elaborate upon the CAD design and thoughts and concepts behind how we decided to implement these constraints. This is the chassis. This is an overall view of the full assembly with the main hull and the turret system on top. So this is the inside of the chassis. The inside of the chassis has on the bottom 4 permanent mounting points that can be used to swap out different designs for the 2 brackets that you see. The one in the front is the bracket for the breadboard, and as you can see, it has inset holes so that the bolts can bolt it appropriately and be flush with the surface so that the breadboard can fit and not take up too much vertical space. The breadboard we use to connect all of our electronics and create our circuitry. In the back, we have a 3D printed bracket for the water reservoir to use its weight to add pressure to the pressure sensor. This pressure sensor is set in that internal square on the inside where we have a smaller circular extrusion to the water tank that would allow the pressure pad to sense these changes in weight. As well as all around the sides, you'll see a lot of holes and mounting points. These are for the external drive linkages. So this is how the road wheels extend lower than the the bottom part of the chassis, and then all the way at the back you have the 6 mounting holes for the drive motors to be mounted very securely. And in the front, you see a cutout for a slot. This is so that we can tension the idler wheels properly. So we can install the tracks, and then we increase the length of the distance bolt connecting the idler wheel to the front road wheel. This way we can have that tension that allows the tracks to work smoothly. And then to talk about more about the design for manufacturability, one constraint that we ran into was that the whole chassis design and sizing was too big for your typical 3D printer. Therefore, we cut it in half and then added an internal flange, much like a lot of the pipes you'll see outside. This internal flange has various mounting points to secure each side to each other, and as well as adding some mounting points to the top or all around so that we can mount the caps on top. And as well as some hole cutouts for the ultrasonic sensor and thermal camera sensor in the front. And now these are the drive linkages I was talking about. So it has 2 bolts connected to the top part. This way it does not rotate upon one point. It maintains its stiffness. And the one on the right, which is for the front, has that it's a bit modified on the top part so that you can insert the distance bolt and connect it to the idler wheel. And this idler wheel has a bolt going through all the way and connects to a capture nut inside a small block on the inside of the chassis. This allows it to secure itself to the chassis while also still being able to move left and right.
Here we have the CAD design for our bearing mount. Um, there are 4 inset screw holes, and that's where our stepper motor is going to be mounted into. The plus sign looking thing is how the turret plate is secured by the stepper motor, and the inset circular holes are where the bearings will sit into. In this slide, we see the turret being attached and where the pump and the servo will be mounted onto. The back side of the plate is where the pump is attached to, and the front side of the plate is where the turret is attached to. Since the turret was initially just bolted to one side of the servo, we added a bearing block on the other side, farthest from the viewer, and that way the turret is stabilized in both directions.
All right, and then here we have an image of the internal wiring for our tank. Thankfully, the chassis was built to measurement, so all of our components can fit very nicely within here. We have the solderless breadboard right there and all of the different electrical components sitting within. While the wiring is a little messy and all over the place, we did successfully fit everything into there, making sure to check for their electrical readings and such to make sure everything can still function properly while still being maintained within the structure. So, yeah.
Lastly, I wanted to talk about our actual demonstration of our product. As we finished our product, it was more appropriate to split our demo into 2 parts. This was mainly because we faced many troubleshooting errors in programming. And so right now we see our tank drive demonstration just to show that we were able to actually get our tank to, move. And in the video, you can kind of see that our turret base looks a little flimsy and moves as our tank takes turns. And this was because our stepper motor was unable to be programmed correctly in the end. As mentioned before by V, the stepper was supposed to pan 180 degrees to the left and 180 degrees total to the left and to the right as the thermal camera searched for flame temperatures. However, again, since the stepper motor was unable to work ultimately on the day of demonstration, it caused our base to kind of not be as secure as we wanted it to. Next, we have our demonstration of the tracking and extinguishing of flame.
Just to add on to what Angie just said, another design flaw of the stepper was the stepper that we were using was a bit undersized in terms of torque power. It was rated for 13 Newton centimeters, so which was not enough torque for the that heavy turret base that was mounted on top.
Continuing with the tracking and extinguishing demonstration, our turret system and integration also experienced a lot of troubleshooting problems with the coding. And although in the video you could see that our actual pump and turret system is working when a flame is present in front of the thermal camera view, you can also see that the accuracy of the actual extinguishing of the flame is pretty inaccurate. And this was mainly due to the fact that we did not really have the chance to get our calibrating in our turret aim with the turret in its final mounted position. However, this demo does do a great job of showing that we were actually able to create a turret and pump water system to detect and aim at a flame when present. Thank you for listening. I hope you enjoyed our ME 106 spring semester project. And yeah.